right, what I'll be talking about today is a relatively new technique for partitioning water vapor and CO2 fluxes by analyzing high-frequency time series of their concentrations. I'll spend some time at the beginning just discussing the technique, giving some background, and I'll go into some case studies and hopefully focus on some of the more interesting results that we get. So there is a current need for partitioning fluxes. When we measure fluxes like with eddy covariance over the top of the canopy, for carbon, what we're measuring is the net ecosystem exchange, which is really a combination of two different fluxes. We have gross ecosystem productivity, which is the downward flux of CO2, and we have ecosystem respiration, which is releasing CO2 to the atmosphere. Similarly, when we're measuring the water vapor flux, which is evapotranspiration, that's comprised of two different things, transpiration and direct evaporation. So these are two distinct processes in both cases being driven by distinct forcing variables. And it's important to understand how we could partition those to understand what the driving forces are behind them and how they respond. So people have been using different approaches. Chamber measurements, for example, have been used to measure respiration fluxes at the forest floor, as well as the direct evaporation fluxes. Sap flux measurements are used on the water side to measure transpiration, and then you could difference what you measure with eddy covariance to get at the bare soil evaporation fluxes. Isotopes for both CO2 and water vapor, both O18 and deuterium. And on the CO2 side, you could use extrapolation of nighttime data that are applied to the daytime data to do that partitioning. So what I'll be describing today is a method that can actually do both these at the same time. It could separate the CO2 fluxes and the water vapor fluxes. And it's based on what goes on at the leaf scale, this exchange between water vapor and CO2, which is the topic of this session, this coupling of water and CO2. We could use that to our advantage to do this partitioning. So we have carbon being taken into the leaf at the same time that water vapor is being released. And we could take a look at the ratio, the carbon flux to the water vapor flux due to transpiration. I'll define that as a water use efficiency, so it's a leaf level water use efficiency. And that's being driven by gradients in the CO2 from the interstomatal CO2 concentrations to the external CO2 concentration, and similarly with the internal and external water vapor concentrations. Now we can see this when we look above the canopy at measurements made of CO2 concentrations and water vapor concentrations. So this shows a movie of a time series collected over 50 seconds. It's sped up. Each measurement is collected, the frequency of collection is 10 hertz. And you can see that the CO2, which is in green, and the water vapor, which is in blue, are almost a mirror image of one another. So when CO2 goes up, water vapor goes down, and vice versa. So there's a very strong correlation. That's reflecting the leaf level exchange that's going on. It's not a perfect correlation, though. There is a breakdown in that correlation, and that's behind the methodology that I'll be describing. Some background in similarity theory. So Monod-Bukov similarity theory says that the scalar statistics measured at a particular point in space are governed by a finite number of things, like the magnitude of the surface fluxes, surface shear stress, buoyancy properties, and then height within the atmospheric surface layer. An implication of this that was shown by Hill in 1989 is that scalar quantities measured at the same position should exhibit perfect correlation. So this is a statement of Flux-variance similarity. And there's been work on that going back to the 80s, or the 90s, and probably even before, some involving Gabby Catul, mostly looking at correlation between temperature and water vapor. So here I'm focusing on correlation between water vapor and CO2. This is just a thought experiment. So let's assume that we just have stomatal exchange going on. So we have CO2, we have photosynthesis, and we have transpiration going on. If we were to look at a time series of the CO2 concentrations measured above the canopy for, say, over the course of 20 minutes or so, it might look like this. The water vapor concentrations that we measure would be a true mirror image of the CO2 concentrations. So if we plot one against another, the water vapor concentrations on this axis, CO2 concentrations on that axis, we would get a perfect correlation. And the slope of that relationship would be the water use efficiency of the vegetation. The correlation coefficient between those two would be -1. So we have perfect anti-correlation. And any perturbation from the mean value of CO2 would scale by the water use efficiency with any perturbation from the mean of the water vapor concentration. Now let's assume that we have the stomatal exchange shut off, and all we have are non-stomatal fluxes. So we have direct evaporation going on, and we have respiration going on. The CO2 time series that we measured above the canopy would look like this, might look like that, and the water vapor time series might look like that. So there we have a perfect positive correlation. The correlation coefficient between water vapor and CO2 would be +1. In reality, when we take these measurements, we have both things going on. So we have a superposition of the stomatal exchange with the non-stomatal exchange. And what that leads to is a breakdown in the correlation of those water vapor and CO2 measurements that we make. So that increases, it decreases the correlation. So the correlation becomes less than perfect. And it also deflects the slope away from this line of water use efficiency. So those are two clues that we could use to do the partitioning. Going into the theory, so propose a modified Reynolds averaging. So we can consider any CO2 perturbation from the CO2 concentration to be due to perturbations caused by photosynthesis and respiration. There's no way to measure those, but let's just assume that that is the case, which I think is a pretty good assumption. We can do the same thing for the water vapor fluctuations. So some of those fluctuations are caused by the transpiration, some are caused by the direct evaporation. And then we could take a look at the variance budget for CO2, which is comprised of the photosynthesis and respiration. Because they're being transported by the same or similar eddies, they will be correlated, so we have to also consider their covariance as well. And we do the same thing for the water vapor concentrations. So based on the flux-variance similarity implications, perturbations for CO2 are scaled through water use efficiency, perturbations by the water vapor. The standard deviations also scale through the water use efficiency, as well as the variances. And then we have those perfectly negative correlations between the stomatal exchange, perfectly positive correlations between the non-stomatal exchange, and then the cross correlations between the stomatal and non-stomatal exchange are the opposite of one another, whether it's transpiration or CO2. We could plug those into the variance budgets here, and we could add some more formulas for the water use efficiency being defined by the total flux of photosynthesis and transpiration, that ratio. And we could plug it into this equation right here, which isn't solved yet. You can see that water use efficiency is on both sides of the equation. But in practice, this is the equation that is solved numerically to come up with a solution. It does have an analytical solution. You can see it is a quadratic, so there could be multiple solutions, but we could get rid of some by throwing away the nonsensical imaginary ones and ones in which variances are negative, for example. And it's most often the case that we end up with one solution. So the only information needed to partition water vapor and carbon dioxide fluxes is the leaf level water use efficiency, which we could get at by extrapolating from our measurement location above the canopy down to the canopy level using a log law, and by considering the internal and external CO2 concentrations. So I've gone through an example, just a qualitative example of what's going on here. I've gotten to some of the mathematics. The question is, does it work? As my former postdoc advisor would say, the proof of the pudding is in the cake, which I'd never really understood what it meant. But you always use that in the context of we need to throw some data at this idea. So we do that here for the case study. This is a cornfield near Beltsville, Maryland. It's operated by the U.S. Department of Agriculture, where a flux tower is set up that's measuring water vapor and CO2. And what we find here, when we look at the correlation coefficient between the CO2 and water vapor over the course of the growing season, starting out like this, very low leaf area index. And then over the course of the growing season, of course, that increases. By the end of the growing season, it looks like this. So the correlation coefficient starts off positive. That's because it's non-stomatal exchange that's dominating at the beginning of the growing season. And then you can see at some point it flips down to that negative correlation, which is indicative of the stomatal exchange. These are the actual measurements of the CO2 flux and the water vapor flux. And these are what they look like when they've been partitioned into photosynthesis and respiration. I'll spend most of the time focusing on the water vapor. So again, the measured water vapor fluxes are partitioned into transpiration and direct evaporation. You get this ramping up over the course of the growing season of transpiration. And you can see it with the direct evaporation, you get these ramp down effects, which I'll describe in a little bit more detail later. Zooming in on some of, these are 4-day periods in the post-planting period, early to mid-growing season, late growing season. Blue line shows the measured water vapor flux. Those blue asterisks is the direct evaporation. So early on, direct evaporation accounts for most of the water vapor flux that we're measuring. When we move through the growing season, that portion that is coming from direct evaporation gets lower and lower, at least according to the results from this partitioning technique. What this shows are daily values from over the course of the 60-day growing period. Here you can see the total evapotranspiration partitioned into transpiration and direct evaporation. And generally you see this transfer over time going from mostly direct evaporation at the beginning to mostly transpiration towards the end of the growing season. The other thing that pops out is every time you get a rainfall event, you get this dip down in the transpiration, and that's filled in by more direct evaporation. Okay, you can see that just about every time you get a rainfall event. Now we could zoom in to those particular periods. This happens to be a wet period, so the potential evapotranspiration is about equal to the actual transpiration. So there's a lid on how much evapotranspiration can take place. Here you can see the direct evaporation accounts for maybe half of the total ET. On day 1, you get this rainfall event between day 1 and day 2, and the direct evaporation really takes off. That means that there's less transpiration on the second day. And we find that that is correlated. There's some relationship with the leaf area index, which makes sense. The more leaf area you have, the more interception story you have. But it is kind of interesting how you see that there is this trade-off effect between the direct evaporation and transpiration. So when you get these rainfall events, the next day the transpiration is decreasing. We look for some things that make sense when we do these partitioning. This happens to be a period of 20 days right here where we get no rainfall. So this is a dry down period. We've just extracted the direct evaporation and plotted the cumulative evaporation as a function of time to the 1/2 power. We'd expect if we were to use a Richards equation, apply a Boltzmann transformation, that the bare soil evaporation would scale with time to the 1/2. And in fact, it does. And when you take a look at the slope, that gives you a desorptivity value that is very similar to what other people have reported under bare soil conditions for that particular soil type. With a transpiration, that doesn't scale with time to the 1/2, nor should it, because it's not being driven by the supply of water to the surface. It's being driven by variable atmospheric forcing. When we want to measure canopy conductance, often what is done is by inverting the Penman-Monteith equation. These are the results that you get just by taking the bulk measured water vapor flux. But really, to understand how the ecosystem is responding to forcing, we really just want to concentrate on that transpiration flux only to get at the canopy conductance, and you can see that they differ by quite a bit. I said I would focus mainly on water vapor, but I have a couple slides here with the carbon dioxide partitioning. Again, for those 3 portions of the growing season, those open circles are the photosynthesis fluxes, and the asterisks are the respiration fluxes. And I think that this is a really nice finding here, where we're just focusing on each day of the growing season, the respiration. this is the way that it would be traditionally measured during the nighttime. We know photosynthesis shuts off during the nighttime, but we see a lot of scatter. There's been a U star, a friction velocity thresholding applied to this. And even so, there's even times where you get a negative respiration during the nighttime. And there's some missing periods here because there was inadequate turbulence. Not enough periods went above the U star threshold. Now, okay, so that's the traditional way to do it. This is by taking the daytime data and finding the respiration flux. And you can see it's a lot more stable. You get these increases, and those are associated with rainfall. So when we have rainfall events coming down, that additional soil moisture spurs the microbial activity, and you see these pulse events take place in the respiration. You get a general increase over the course of the growing season in the respiration, and that's despite the fact that you get a decrease in the soil moisture and soil temperature. But that's mainly being driven by the increase in autotrophic respiration. So if we were to put in the model maintenance and growth respiration, that's what's driving the increase that we see over the growing season. So that respiration is not controlled by the two things that are normally used in modeling, the soil moisture and the soil temperature. Another case study in a more arid region now. This is the Barex 08 experiment. It's a cotton field near Bushland, Texas. So here, irrigation is used to supplement the natural rainfall. This is the time series over the growing season. Yellow are the irrigation periods. We have plotted here the ratio of transpiration to the total evapotranspiration. Of course, that increases over the course of the growing season. At this site, we did have Nurit Agam taking measurements with microlysimeters of the bare soil evaporation. And so there's not great coverage here, but what's plotted there are the estimates of this ratio of transpiration to total evapotranspiration estimated with these microlysimeters based versus the partitioning technique. Again, there's no calibration involved. This is a truly independent comparison of these two methods. This shows the cumulative fluxes over the course of the growing season. This is rainfall and irrigation, which is this blue line right here. And it's breaking down the cumulative fluxes into the transpiration and direct evaporation. They sum up pretty close to the rainfall and irrigation. There is some difference, and that could be due to change in storage in the soil moisture, any drainage from the root zone, or maybe Eco-hydrology underestimation. Ideally, this transpiration, these blue bars right here, should be hugging this line right here. So you want any water that goes into the soil to be used for transpiration by the plants, not lost due to direct evaporation. Some people have argued in the literature recently that direct evaporation really isn't wasted because it has the effect of humidifying the canopy. So that results in less transpiration losses per unit carbon uptake. But with the partitioning results, that's something that we could evaluate. So what's plotted here is a direct evaporation rate and water use efficiency on the y-axis. And we find that with greater evaporation, there is an improved water use efficiency. And we could plug this in, just do a back-of-the-envelope calculation, which I won't get into. But what we find is that the direct evaporation, for every 6 millimeters wasted, there's 1 millimeter credited for biomass production. So there is some truth to this idea that direct evaporation isn't truly wasted. It's mostly wasted. We find here that it's 80 to 90% wasted water. So I showed that example of comparing methods for the partitioning. Here's another example. Colleague Kelly Kahlers and his group, Stephen Good, has this study that's in revision right now. Done in Kenya, where they irrigated an area, a grassland area. They had a Eco-hydrology tower set up, along with a cavity ring spectrometer. to get at the partitioning of the water vapor using the isotopes. After they did this irrigation, they found this increase in the LAI of the grass. They had this kind of freak rainfall event that happened in day 8. They didn't really expect this to occur. But they were able to get some results with the isotopic flux partitioning, shown with a blue line here for both transpiration and evaporation. And the dashed red line is results with a flux-variance similarity. We find that they agree okay. The one big difference between the two is in day 8. That's the time when this rainfall event arrived. The flux-variance similarity theory would say that there's a lot more bare soil evaporation that went on after that rainfall event arrived, and a reduction in the transpiration. I'd like to finish up with this third case study, a more local example. This is a vineyard in the Negev Desert. It's a pretty remarkable site. It's only 100 to 150 millimeters per year of rainfall. So again, they have a flux tower set up where they're measuring at high frequency the CO2 and water vapor concentrations. Here are some results from this site. Latent heat flux is plotted over the course of, this is a 70-day growing season. Each time that this partitioning technique was able to identify, was successful, you'll see a dot there that represents the direct evaporation. And in terms of the fraction of ET, this is about as good as it gets in terms of irrigation. You see that about 90% of the evapotranspiration flux is coming from direct evaporation. It does kind of get worse as we move into the second half of the growing season, but that's still about 80%. Looking into why there was that reduction, I think it's pretty clear if you look at the irrigation record. For some reason, the farmer decided to increase the frequency of the application of irrigation in the second half of the growing season, probably to avoid water stress by the grapes. But that did result in a reduction in the efficiency by which the water was used by the vegetation. So what I showed were many examples from managed systems, agricultural systems. We're interested in applying this to natural systems. We have this flux tower that we had set up back in October through December in Botswana. So one of the reasons I started off with these agricultural systems is because they're pretty well described and well studied, single type of vegetation. It does get more complex when you have this mixed vegetation. So here we'd have to account for the fact that the water use efficiencies are very different for C3 and C4 vegetation. I think mathematically it can be done. You just have to plug into the series of equations the water use efficiencies separately for the grass and the tree cover. And then you could look at questions like, what effect does burning have on the tree grass transpiration? Here where we have the burning, we get the hydrophobic soils. It's analogous to the soil sealing that has been described by some other people. And questions like, is there an optimal vegetation structure for maximizing the landscape scale ratio of transpiration to the total evapotranspiration? And then finally, advantages of the approach, very simple theoretical approach conceptually. It relies on routine eddy covariance measurements. You don't need any extra instrumentation to do this. And limited ancillary information is required. In fact, the only thing that you need to put into this technique is the water use efficiency of the vegetation at the leaf level. Next steps, extend the method for use with mixed vegetation, improve the water balance models, which are notorious for not doing a very good job with bare soil evaporation and how they handle interception store. And then apply it to other sites for eco-hydrological applications. So if anyone is interested in applying this to their eddy covariance data, please let me know. I have the code available. I'd be happy to share with people. So I'd like to thank some people, especially Narit Zagam for the vineyard data, and some of the other folks at the U.S. Department of Agriculture, and some co-authors on the couple papers that I mentioned earlier.
couple of quick questions before, I guess, signs that people are waiting outside. Okay, Gabi.
A quick question, Todd. The flux variance method typically assumes that all the variance that you see in the concentration is due to flux from the surface. Now, there's been a number of papers that have suggested that the variance may be more contaminated by entrainment processes. A little bit of non-stationarity will have a huge impact on your variance. Did you do any post-processing of the data to remove those, or so that you could better couple the flux, the local flux to the local variance, or did you just use the raw data, or was it important at all?
Yeah, you're exactly right. And you're right, there have been other papers that have mentioned some other causes of breakdown in flux variance similarity, things like non-steadiness, entrainment, horizontal heterogeneity. In fact, in doing this I apply wavelet analysis to basically peel off some of the lower frequency information on the data until we get to a point where it's just more the high frequency data that doesn't have the impact of some of those issues.
So may I suggest that you would have computed the co-spectrum of the flux, identify the frequency at which it is peaking,
right,
and actually filter the variance up to that point?
At that point, yeah, that's a good idea.
Maybe I can add a quick question. You know, in this region, we see a lot of situations where VPD is changing dramatically. And what we see when we look at the carbon-water relationship, we see that VPD, the stomatal conductance respond to VPD very strongly, but because stomatal close when VPD goes up, actually the water flux stay completely flat. So this relationship will not be apparent in this kind of environment.
Yeah, so, well, I think it would still work. The key factor, though, is getting the water use efficiency, the leaf level water use efficiency nailed down. And vapor pressure deficit does influence the CI to CA ratio. So that's something, in working with the vineyard data, that we accounted for. We thought that was pretty important to get that impact of vapor pressure deficit on that CI-CA ratio.
Okay, I think with this we complete the session, and let's thank all the speakers.
Okay, we will leave lunch for 1 hour.